The wind coming off the Kennebec River in January is not merely cold. It is a physical force that searches for any gap in a parka and bites down on the skin beneath. Here in Bath, Maine, the winter air smells of salt water, diesel exhaust, and the metallic tang of grinding steel. It is 4 in the morning, yet the floodlights bathe the shipyard in a harsh, artificial noon. From the vantage point of the Carlton Bridge, the sprawling complex of Bath Ironworks looks less like a factory and more like a fortress under siege, surrounded by cranes that loom like siege engines against the dark sky. Inside the yard, the noise is a constant, rhythmic percussion. It is the sound of American heavy industry at work. Shifts here do not truly end. They blend into one another. A ceaseless relay race to turn blueprints into the most sophisticated surface combatants on the ocean. The subject of this labor is the Arleigh Burke-class destroyer, a vessel that represents the convergence of brute naval architecture and delicate silicon engineering. To understand the birth of one of these ships, one must step away from the water and move inland to the fabrication shops. This is where the ship begins, not as a keel laid on a slipway, but as raw plates of high-tensile steel stacked in the yard. A material handler watches as a magnetic crane lifts a 40-foot plate, shaking the snow from its surface before feeding it into the processing bay. The construction philosophy employed here is known as modular build. In the days of the Second World War, ships were often built from the bottom up, piece by piece, directly on the launchway. Today, that method is obsolete. Instead, the destroyer is sliced conceptually into dozens of massive, three-dimensional puzzle pieces called modules or blocks. These blocks are constructed independently, often upside down or on their sides to allow welders to work with gravity rather than against it, before being joined together later in the process. Inside the Harding's fabrication facility, a few miles up the road from the main riverfront yard, the atmosphere is smoky and loud. Computer-controlled cutting torches dance across the steel plates. They follow digital files generated by design teams that may be sitting in offices hundreds of miles away. The plasma cutters hiss as they slice through inches of steel, as if it were construction paper. These cut shapes are the ribs, the bulkheads, and the decking of the future warship. A foreman walks the line, checking the edge preparation on a fresh cut. He explains that the tolerances here are not what one might expect for a 9,000-ton object. They are measuring in millimeters. If a steel plate is cut incorrectly now, it will compound into a massive alignment error when the blocks are brought together months later. The steel must be perfect. Once cut, the flat plates are moved to the panel line. Here, machines and men work in tandem to weld stiffeners onto the plates. These stiffeners look like steel beams running the length of the floor. They provide the structural rigidity the ship will need to survive the violent twisting forces of the North Atlantic. Automated welding heads track along the seams, laying down beads of molten metal that cool into a gray scar, stronger than the steel around it. As the flat panels are welded together to form box structures, the ship begins to take up volume. This is the transition from 2 dimensions to 3. This phase creates the skeleton of the module. It is heavy, dirty work. Welders squeeze into tight compartments, their respirators hissing, the blue light of their arcs casting dancing shadows on the walls. They are building the tanks that will hold fuel, the magazines that will hold missiles, and the passageways that sailors will run through at general quarters. However, a modern destroyer is not just a steel box. It is a vessel that must support life and wage war. This introduces the concept of pre-outfitting. In traditional shipbuilding, you built the hull and then dragged miles of pipe and wire through it. In the modular era, the pipes and wires are installed while the module is still open and accessible. In the assembly halls, pipe fitters wrestle with complex spools of copper-nickel piping. These are the veins of the ship, carrying fire main water, hydraulic fluid, and chilled water for the electronics. They bolt flanges together and tack weld hangers to the overheads. At the same time, ventilation workers install the silver ductwork that will act as the lungs of the ship. It is a choreographed chaos. A pipe fitter works 5 feet away from an electrician who is pulling the initial runs of armored cable. They have to communicate constantly. If the ventilation duct is installed 2 inches too low, the cable tray cannot pass. If the pipe flange is rotated the wrong way, it will block a hatch. The complexity increases as the modules grow. Small sub-assemblies are welded together to form the grand blocks. These can weigh hundreds of tons. Moving them requires a transporter, a multi-wheeled vehicle that looks like a flatbed truck for giants. These transporters slide underneath the steel structures, lift them hydraulically, and creep them across the asphalt at the speed of a slow walk. One particular challenge in the early stage is the integration of the machinery spaces. The main reduction gears and the gas turbine engines are the muscles of the destroyer. These components are not built at the shipyard, but arrive from suppliers across the country. The gas turbines, derivative of aircraft engines, are compact but powerful. The reduction gears are massive, precision-machined assemblies that take the high-speed spin of the turbines and slow it down to drive the propeller shafts. Dropping these engines into the steel modules requires a crane operator with nerves of ice. The clearance on either side might be less than the width of a human hand. Workers stand ready with taglines, guiding the swinging multi-million-dollar machinery as it lowers into the steel canyon of the engine room module. Once seated on its mounts, the machinery is covered and protected. The ship will literally be built around it. There is no easy way to get these engines out once the decks are welded shut above them. Back outside, the winter deepens. Snow piles up against the side of the massive assembly buildings. Inside, however, the work accelerates. The schedule is a relentless driver. The Navy has a specific date in mind for when this hull must enter the water, and that date dictates every swing of a hammer and every spark of a welding torch. The distinct shape of the Arleigh Burke-class begins to emerge in these scattered blocks. The raked bow, designed to slice through waves and improve seakeeping, is built as a separate massive unit. It sits in the yard like a steel monolith, its internal compartments already painted white, waiting for the day it will be joined to the rest of the body. This is the heavy industrial phase, the era of fire and steel. But parallel to this, in clean, quiet rooms far removed from the welding dust, a different kind of construction is taking place. This is the preparation of the ship's nervous system and brain. The Aegis combat system is not just a radar. It is a total weapon system that ties together sensors, weapons, and command logic. While the shipbuilders at Bath are experts in steel, they must also become partners with the electronics experts who will turn this hull into a warship. The interplay between the rough work of structural fabrication and the precision work of combat systems integration is the defining tension of the project. A warped bulkhead is a structural problem, but a warped bulkhead where a radar array needs to sit is a mission failure. As the blocks near completion, the focus shifts to the superstructure, the towering island that will sit atop the deck. This is where the famous Spy-1 radar faces will reside. The fabrication of the deckhouse module requires even tighter tolerances than the hull. The radar arrays must be positioned with absolute precision to ensure they provide hemispherical coverage without blind spots. A deviation of a fraction of a degree in the angle of the steel mounting plate can degrade the system's tracking ability at long range. As the winter turns to a muddy, freezing spring, the shipyard prepares for the major consolidation. The individual blocks, now looking like recognizable slices of a ship, are ready to be brought together. The land-level transfer facility is cleared. This is the stage where the disparate parts will become a whole. The workers zip their jackets tighter and prepare for the heavy lifts. The easy part is over. Now they have to make it all fit. The visual dominance of the Arleigh Burke destroyer comes from its superstructure. It is a raked, angular castle of steel that rises from the main deck, designed not for aesthetics, but for the deflection of enemy radar energy. Building this structure is a departure from the heavy, thick plates of the lower hull. Here, the steel is thinner to save top weight, yet it must be rigid enough to support the crown jewels of the ship, the AN Spy-1 radar arrays. Inside the Ultra Hall, a cavernous assembly building capable of housing these massive structures out of the weather, the deckhouse module sits on temporary supports. It is here that the collision between the industrial age and the information age is most violent. The air is filled with the smell of curing epoxy and fresh paint, distinct from the ozone scent of the welding shops. The defining feature of the Aegis system is the phased array radar. Unlike older radars that used a rotating dish to sweep the horizon mechanically, the Spy-1 uses 4 fixed octagonal faces. Each face is packed with thousands of radiating elements that steer the radar beam electronically. This allows the system to track hundreds of targets simultaneously and instantaneously without the lag of a mechanical rotation. Installing these faces is a surgical procedure performed with cranes. The radar arrays arrive in localized protective crates, looking like artifacts from a spacecraft. The steel openings on the deckhouse, known as the cutouts, have been measured and remeasured using laser theodolites. The flatness of the mounting ring is critical. If the steel is wavy or warped from the heat of welding, the radar face will torque when bolted down, potentially cracking the delicate ceramic elements inside. Ship fitters and machinists work together to machine the landing surfaces. They use portable milling machines that clamp onto the rough steel and shave it down to a mirror finish, accurate to within thousandths of an inch. Once the surface is approved by quality assurance inspectors, the crane begins the lift. The radar array hangs suspended in the air, a dark gray octagon against the industrial lights. Slowly, inch by inch, it is drifted into the opening. Men on scissor lifts guide it with hand signals. There is no room for error. A collision between the array and the steel bulkhead would cause millions of dollars in damage and months of delay. When the array finally seats against the mounting ring, a collective breath is released. Then begins the tedious process of torquing hundreds of bolts in a specific star pattern to ensure even pressure. While the exterior is taking shape, the interior of the deckhouse is being transformed into the Combat Information Center, commonly referred to as the CIC. This is the brain of the warship. In World War II movies, the bridge was the center of command, where the captain peered through binoculars. On an Aegis destroyer, the bridge is for navigation safety. The fighting happens in the CIC, a windowless room buried deep in the protective shell of the ship. At this stage of construction, the CIC is a maze of raised flooring grids and empty console foundations. The challenge here is cabling. A modern destroyer contains literally millions of feet of cable. There are power cables, heavy and stiff as snakes. There are fiber optic lines, fragile and requiring delicate handling. There are radio frequency cables that carry the signals from the antennas to the processors. Teams of electricians swarm the space. They consult complex wire run sheets that tell them exactly which path each cable must take. They pull the cables through stuffing tubes in the bulkheads, which will later be sealed to prevent the spread of fire or flooding. The physical effort of pulling cable is exhausting. It requires coordinated teams heaving in unison to drag heavy bundles through twisting trays. Yet they must be gentle enough not to crush the insulation or break the glass fibers inside. The consoles for the Aegis system arrive wrapped in plastic. These are the user interfaces, the glowing blue screens where young sailors will make life or death decisions. Installing them requires a clean environment, something difficult to achieve in an active shipyard. Temporary walls are erected, and air scrubbers are brought in to create positive pressure zones, keeping the grinding dust and metal shavings out of the sensitive electronics. The contrast is stark. In one compartment, a grinder is smoothing a weld, sending a shower of sparks against a fireproof blanket. In the adjacent compartment, a technician in a clean smock is terminating a fiber optic connector using a microscope. The shipyard must manage these conflicting environments simultaneously. As the superstructure nears completion, it is weighed. Weight control is an obsession in naval architecture. If the ship is too heavy, it will sit too low in the water, reducing its speed and range. If the weight is distributed poorly, the ship will be unstable. Every bracket, every coat of paint, and every box of electronics is tracked in a master database. If a module comes in overweight, engineers must find a way to shave pounds elsewhere, or the ship's ballast plan must be adjusted. Outside the assembly hall, the main hull blocks are being joined on the land-level facility. The grand blocks are moved together on the rail system. The seam where two blocks meet is called the erection joint. Fitting these massive sections together is a testament to the accuracy of the initial cutting and fabrication. When two blocks are brought together, they may not align perfectly due to thermal expansion or slight settling. Shipwrights use hydraulic rams and turnbuckles to force the steel into alignment. They call this fairing the joint. Once the plates are flush, the welders take over. They will make multiple passes, filling the groove with weld metal until the two blocks become one continuous structure. This welding happens around the clock. At night, the glow of the arcs from the hull seams looks like fireflies swarming the steel beast. The installation of the vertical launching system, or VLS, is another major milestone. These are the missile silos, sunk into the deck of the ship. The Arleigh Burke carries two VLS banks, one forward and one aft. The modules for these launchers are deep, extending down through several decks. Dropping the VLS modules in is like inserting a cartridge into a massive gun. They must be aligned perfectly with the ship's reference planes, so that when a missile is fired, the guidance computer knows exactly where it is starting from. As the hull and superstructure are finally joined, a process called stepping the house, the ship truly looks like a destroyer. The crane lifts the entire deckhouse module, weighing hundreds of tons, and places it onto the main deck. This is a critical weld. The connection between the aluminum or steel superstructure and the steel hull must be flawless to withstand the hogging and sagging of the ship in heavy seas. With the major structural pieces in place, the ship is now a recognizable silhouette on the Kennebec skyline. But it is still a hollow shell in many ways. The thousands of pipes and wires that were installed in the individual modules must now be connected across the splice points. This is the great hookup phase. It is tedious, back-breaking work. Workers must crawl into the crawl spaces and bilges to braze pipe connections and splice cables. The shipyard begins to buzz with the testing crews. Before the ship can be launched, the hull integrity must be verified. Compartments are sealed and pressurized with air to check for leaks. Tanks are filled with water. The ping jockeys, the sonar technicians, begin checking the integrity of the bow-mounted sonar dome, a rubber and steel bulb at the very front of the ship below the waterline. The transition from a construction project to a living ship is beginning. The temporary lights strung up by workers are replaced by the ship's own lighting circuits. The ventilation blowers are energized, creating a low hum that will be the background noise for the crew for the next 30 years. The electronic heart of the ship is starting to beat. but it is still tethered to the shore, a captive giant waiting for the water. The unification of the Arleigh Burke destroyer is a process of accumulating mass and complexity until the object becomes too vast for the land to hold. By late summer, the vessel sitting on the land-level transfer facility is no longer a collection of codes and blocks. It is a monolith of haze gray, spanning over 500 feet. The scaffolding that clings to its sides like a steel web is constantly busy with workers. Inside the hull, the hookup phase reaches its crescendo. The focus shifts from heavy structural work to the intricate arterial connections that make the ship functional. This is where the modular concept faces its final exam. The pipes that were installed in the forward module back in January must line up perfectly with the pipes in the midships module built in March. A misalignment of half an inch here requires a pipe fitter to fabricate a custom spool piece to bridge the gap, a time-consuming detour that managers hate. The electrical teams face the most daunting task. The splice breaks between modules involve thousands of individual wire connections. Each connection must be made, insulated, tagged, and tested. Quality assurance inspectors follow behind the electricians, tugging on wires and checking crimps. A single loose connection in a fire control circuit could mean a missile fails to fire in combat years from now. The standard is absolute perfection. Down in the main engine rooms, the alignment of the propulsion train is underway. The gas turbines connect to the reduction gears, which in turn connect to the long propeller shafts that run out the back of the ship. This drivetrain must be aligned to within thousandths of an inch. However, the ship is currently sitting on blocks on dry land. When it floats, the steel hull will flex and settle, potentially throwing that alignment off. To counter this, engineers perform complex calculations to offset the alignment on land, predicting exactly how much the hull will bend when water supports it. They use optical sights and laser manufacturing equipment to set the bearings. It is a gamble based on physics and experience. They won't know if they got it right until the ship is afloat. The Aegis system integration moves from physical installation to power up. The massive generators come online, feeding high voltage power to the switchboards. For the first time, the radar cooling pumps circulate water. The dry air systems pressurize the waveguides. In the Combat Information Center, screens flicker to life, displaying test patterns. The software load is massive. Millions of lines of code that manage everything from the radar pulses to the mess deck inventory. This phase also sees the installation of the soft items. Joiners install the bunks, the lockers, and the galley equipment. The habitable spaces begin to look like rooms rather than steel boxes. The smell of welding smoke is replaced by the smell of floor wax and fresh paint. The ship is being made ready for human habitation. Then comes the preparation for the move. The Arleigh Burke is built on a level surface, but it must enter the river. The transition is a spectacle of industrial engineering. The transfer system involves a grid of rail tracks and self-propelled modular transporters. These computerized hydraulic bogies roll underneath the ship's cradle. On the morning of the transfer, the yard is quiet. The move is slow, almost imperceptible. The hydraulic lifters hiss as they take the weight of the 9,000-ton vessel. The ship rises just a few inches, enough to clear the ground supports. Then, the transporters begin to crawl. The destroyer moves laterally, translating from its build position toward the dry dock or the launch mechanism. It is a surreal sight, a warship sailing through the air across a parking lot. The team controlling the transporters walks alongside, holding control boxes, watching the load sensors on each wheel. The center of gravity must be maintained perfectly. The destination is the floating dry dock. This is a massive, U-shaped vessel in its own right, capable of submerging itself. The destroyer is rolled onto the deck of the dry dock. Once the ship is secured on the dock's blocks, the transporters are withdrawn. The ship is now technically no longer on land, but it is not yet in the water. It sits high and dry on the floating platform. For the older ships of the class, or depending on the specific facility configuration at the time, the launch might have been a dynamic slide down inclined ways. That visceral, violent slide where the ship crashes into the river sideways, or stern first, is the romantic image of shipbuilding. However, the sheer complexity and weight of the modern Aegis destroyer, packed with sensitive electronics, favors the gentler float-off method of the dry dock. It reduces the shock to the radar arrays and the sonar dome. As the launch day approaches, the exterior of the ship is given its final dress. The hull numbers are painted on the bow in white block and shadow. The draft marks are verified. The anchor chains are installed, massive links of steel that weigh hundreds of pounds each. The propeller blades, currently covered to protect their polish, are inspected one last time. The shipyard workers begin to clean up. The scaffolding is stripped away, revealing the clean lines of the hull. Banners are hung from the railings. The ship is transformed from a construction site into a ceremonial object. The crew of the ship, the sailors who will actually take her to sea, have arrived. They have been working in building offices nearby, training and organizing. Now they begin to walk the decks, familiarizing themselves with the geography of their new home. They work alongside the shipyard civilians, a blending of blue coveralls and blue camouflage uniforms. The tension in the yard is palpable. The launch is the finish line for the builders. Once the ship hits the water, it belongs to the river and eventually to the ocean. The physics change. The ship becomes a live thing, subject to tides and currents. The night before the launch, the dry dock is moved into position in the deep channel of the Kennebec. The final checks are made on the sea valves. The hull is inspected for any scratches or imperfections in the anti-fouling paint. Under the floodlights, the ship looks immense, a towering wall of steel looming over the dark, cold water of the river. The stage is set. Launch day in Bath is a convergence of community, industry, and heritage. The town, which exists largely because of the shipyard, turns out in force. The viewing stands are draped in red, white, and blue bunting. Civilians crowd the public parks along the riverbank, while VIPs, naval officers, and politicians gather on the platform near the bow of the ship. The atmosphere is a mix of a political rally and a football tailgate, underpinned by the serious gravity of military tradition. The sponsor of the ship, usually a woman with a connection to the ship's namesake, stands ready with the bottle of sparkling wine. This tradition is centuries old, a superstition that demands a sacrifice of wine to ensure the ship's luck. The bottle is encased in a mesh breakout sock to prevent glass from flying into the crowd, and it is tethered by a ribbon. Speeches echo over the PA system, praising the workforce, the naval service, and the legacy of the Arleigh Burke-class. But the eyes of the shipbuilders are on the tide. The Kennebec River has a strong tidal flow, and the launch must be timed perfectly to ensure there is enough depth and that the current is manageable. The dockmaster communicates with the tugboat captains via radio. The tugs, stout and powerful, churn the water nearby, waiting for their moment to take control of the newborn giant. If the launch utilizes the floating dry dock method, the drama is slow and hydraulic. The valves on the dry dock are opened, and water floods the ballast tanks. Slowly, imperceptibly at first, the dock begins to sink. The destroyer, sitting on its blocks, descends with it. The water rises up the side of the dry dock walls. The critical moment is float off. This is when the buoyancy of the destroyer overcomes gravity. The water creeps up the hull, past the keel, past the sonar dome, reaching the waterline. Suddenly, the ship is no longer resting on the wooden blocks. It lifts free. A cheer goes up from the workers closest to the edge who can see the gap form. The ship is floating. It is now a waterborne vessel. In the older, more kinetic style of launch, still remembered fondly by the veterans of the yard, the ship would slide down greased ways. The trigger would be pulled, the wine bottle smashed, and the massive hull would gain momentum, sliding stern first into the river, generating a massive wave that washed over the opposite bank. The ship would roll heavily to one side before righting itself, a terrifying moment of physics asserting itself. Regardless of the method, the moment the ship enters the Kennebec is transformative. The tugboats immediately move in. Their job is to wrangle the drifting Leviathan. They push their padded bows against the gray steel, their engines roaring as they fight the current to stabilize the destroyer. Lines are thrown and secured. The ship, which has spent its entire existence as a stationary object on land, is now moving with the fluid grace of a boat. The crowd erupts. Sirens wail from the shipyard cranes. Air horns blast from nearby vessels. It is a moment of pure industrial triumph. The welders, electricians, and engineers watch with a proprietary pride. They know every inch of that steel. They know the frustration of the difficult welds and the satisfaction of the completed tests. Once the ship is stabilized, it is towed to the outfitting pier. The launch is not the end of the work, but it is the end of the beginning. At the pier, the final phase begins. This is the activation of the combat systems and the sea trials. In the weeks following the launch, the ship wakes up fully. The gas turbines are fired for the first time, sending a jet of heat exhaust out the stacks. The radar radiates into the atmosphere, tracking commercial airliners hundreds of miles away as a test. The sonar pings into the murky river water. Eventually, the ship casts off its lines for alpha trials. It moves down the Kennebec, past the doubling point light, and out into the open Atlantic. This is where the builders prove their work. The ship is run at full power, carving deep turns that heel the deck over at sharp angles. The engines are thrown from full ahead to full reverse to test the stopping distance. The guns are fired. The anchors are dropped. Back at Bath Iron Works, the slipway where the ship was built is already occupied. The first modules of the next destroyer are already being laid out. The cycle continues. The steel plates are being cut. The sparks are flying, and the winter wind is blowing off the river. The Arleigh Burke destroyer, now a commissioned warship, sails away from Maine. It carries with it the labor of thousands of hands, the torch operators, the cable pullers, the painters, and the software engineers. It is a piece of sovereign American territory, a floating city of steel and silicon, designed to go into harm's way. But its soul will always remain in the frozen, gritty shipyard on the banks of the Kennebec, where it was forged from raw metal into a living thing.